Hello everyone, and welcome back. Now, in the previous lecture, I introduced you to some of the basics of discrete time dynamical systems, or difference equations, as they're sometimes known. Now, I gave you a couple examples, and maybe I helped you to get your bearings, but in this lecture, I want to go deeper. And in particular, what I want to focus on are one-dimensional difference equations. So that means that your state space has only one variable in it. Now, what I'm going to do is I'm going to walk you through some modeling problems, and I'm also going to show you a powerful graphical method that can help us to understand solutions to these equations. Now, this is just like what we did with phase line diagrams. You're going to see that there is an analogy that extends to these difference equations. But let's start with a modeling problem, okay? Let's start simple. Let's imagine that we have a population of yeast, and we observe that this population of yeast is growing at about 10% per hour, okay? And we actually counted, we know that, when you start counting, the initial amount of yeast is 100,000. So that's the size of your population when the clock starts, okay? And so we can model this as a difference equation, as a discrete time dynamical system. We are going to assume that we are checking the population every hour. So that is our discrete hopping process, right? There is no assumption of sort of what's happening in between. We are really just walking ourselves from 0 hours, 1 hour, 2 hour, 3 hour, 4 hours into the future. So let's start taking a look at this. Well, one thing that we do in mathematical modeling, especially when it comes to these biological populations, is to look at what's called the relative growth rate. So in this case, the relative growth rate R would be given by the change in your population divided by the current population, right? So this is something we've already seen. We've talked a lot about relative rates. In particular, we saw these come up with sensitivity analysis in our optimization portion of this course. Now, in our case, we have that our relative growth rate is fixed at 10%, right? So in our case, it does not depend on when we are checking. We have this assumption that this is going to be equal to 0.1. So our growth rate is 10% per hour. Again, we're moving n by hours here. But this allows us to write our discrete time dynamical system as 0.1 x to the n, x of n. In this case, x of n is our population of our yeast at hour n. It's only one-dimensional. And now we've got a pretty little difference equation. In particular, if you wanted to, you could rearrange this thing and you could say, okay, the population of the yeast at the next hour is going to be 1.1 times the current population of the yeast. All I did was carried this over and I reformulated this as a proper stepping algorithm. Now, the other piece of this that I gave you already is that you have initially a population of 100,000 for your yeast colony. Now, we've already seen how this works in the last example, right? We can actually explicitly solve this thing. We know that the solution to this iterative process with this initial condition, so our population of yeast at n hours in the future, is going to be 1.1 times to the power of n. This is taking the role of my 1 minus lambda, if you remember from the previous video or if you look back in your notes, and then times 100,000. And so maybe we were asked the question, how much yeast are you going to have after 4 hours? So we could do this. We could say after 4 hours. Well, this would be x of 4. And in this case, it is just 1.1 to the 4th power multiplied by 100,000. In this case, it's 146,410. So our population of yeast has gone up by about 46,410 in its population. Now, I could also ask, when does the population double? Does population double? This is, again, a perfectly achievable question for us because we want to find, so we want to solve x of n equal to 200,000. We want to know when we have double what we started with. Well, again, maybe you've seen these before. You probably encountered questions similar to these in your maybe introductory calculus courses. And so essentially, I'm going to take this equation right here. I'm going to set it equal to 200,000. This is the same as taking 1.1 to the n is equal to 2. That's all I did was divide off the 100,000 here. Now it's really just a little bit of fun with logarithms. This gives you that, n is equal to the natural logarithm of 2 divided by the natural logarithm of 1.1. And in this case, this is somewhere around 7.27. Okay, so in our case, since we are only checking at discrete time intervals, we would have to check at the 8th hour into the experiment, because if we looked at 7, we won't get full doubling of the population, but when we come back at hour 8, we will have more than double of what we initially started with, right? So this is where the sort of discrete aspect of this comes in. If this was a continuous time system, we could easily just say 7.27 hours, right? But there is a discrete iterative hopping process taking place in the background. Now, I have full confidence in you that this is probably a relatively simple problem. But the question is, what happens if we can't actually solve the problem explicitly? How do we get some information out of it? And again, I will remind you, at least for some of the continuous time systems that we've looked at, we have methods of understanding them. For one-dimensional systems in continuous time, we have the phase line method. For two-dimensional systems, we have the phase plane method. And we saw that these essentially just come down to our understanding of derivatives. Now, in this case, we don't have any derivatives. So we can't really say things like increasing or decreasing, but there is still a graphical method that we can put to use here. Okay? So let's first begin by formulating a more complex model for my yeast population. Okay? So again, think about my yeast population. What this is saying is it's just going to grow without bound, right? Eventually, according to this model, my population of yeast could be 1 million, it could be 1 billion, it could be 1 trillion. I mean, it could just take over the entire universe. Of course, this is not feasible, right? This is just like our whales that we looked at earlier with continuous time systems. There is an internal competition for resources in space that is not being modeled in this case, right? So the question is, how do we update our model in order to have some kind of accounting for this, this competition? Well, let's go back to our growth rate equation, right? So remember, the key piece of this was that we assumed that we have a constant growth rate of 10%. So no matter how much of our yeast population we had, we're always just going to see 10% more the next hour we come and look at this. Well, what if we augment this a little bit, okay? What if we say that the growth rate is going to be, okay, some constant rate r, but this constant rate goes down as the population goes up, right? So if you imagine maybe you have your yeast population in a petri dish or something like that, right? There's only finite amount of room and resources that these yeast can take up. So the more yeast you have, it's starting to get very, very crowded in there, and they don't really want to reproduce that much anymore, right? There's not a whole lot of room for anybody new. So that would mean that the reproduction rate, the rate in which the population increases from hour to hour, is going to go down if the population is very large. If the population is so large that you have overcrowding, right? People are on top of each other, nobody can move, then nobody's reproducing anymore. And in fact, you're sort of dying out. You're competing for resources so much that there's just not enough for everybody. So in this case, you have a constant growth rate, but this constant growth rate is adjusted according to your current population. So in my case, K is what's known as the carrying capacity. Again, we saw this when we looked at the whales problem and even the trees problem from earlier with the continuous time systems. This might be, for example, the population of yeast that can be supported, say, inside of my petri dish. The maximal number of the yeast population that can exist in there. And so what this says is that I will continue to grow at some rate so long as I am below the carrying capacity, right? If the yeast are below carrying capacity, then they have a positive growth rate and they still want to grow up. But if I go beyond my carrying capacity, if xn is bigger than k, this becomes negative and my yeast population wants to contract. It says there's too many of us. We gotta call the herd a little bit. But in this case, now we have a much more realistic model to work with. So for example, this model will look like this. So we can get x of n plus r x of n 1 minus x of n over k. So now we've got a quadratic function, right? This is quadratic in the nonlinearity or in the yeast population x. In this case, r is going to be positive, k is going to be positive. The exact values don't matter that much. But what I really want you to notice here is that now I can't solve it exactly. I cannot just say x of n is equal to 1.1 to the n times 100,000 anymore. So the question is, what could we do? How can we handle this thing? Well, this is where my graphical method comes in, okay? So here's what I want to do. I want to sketch out my curve here, okay? So this would be, if I use the notation from the previous video, this is x of n, f of x of n. Now, that means that I could sketch out my f of x function here. Let's imagine that r is relatively small. So let's say I've got something that looks like this. Okay, so here's, it's, again, not the prettiest picture you're going to see all day, but let's imagine that this is my function f of x. Okay, so let's say f of x. All right, and what I'm going to do on top of this function, so not only plotting the right-hand side here, I'm going to plot another function, which is just y equal to x. Nothing fancy, nothing special. Okay, so this is y equal to x. Now, the first thing that I want you to notice about these two pictures is that they intersect. They intersect at a very important point. In fact, they intersect at the equilibrium point. Right? So this is exactly the point where there is no change in your system. Now, if there's no change in your system, delta x is equal to 0, which means that x is equal to k. So that means that the unique positive equilibrium point, right? There's a second one at 0 down here. There are two equilibrium points given by the intersections of these curves. This says that if your population is exactly at the carrying capacity, then your population doesn't want to increase or decrease. It's very happy being there. It's in a nice state of equilibrium. Same thing, if there's no population, there's no way you're ever going to be able to reproduce, and so nothing interesting could ever happen. So already we can see an advantage for plotting these pictures, right? Because now, immediately, I can identify where the steady states are. I've got one right here at the carrying capacity K. Now here's the real beauty though, is just like a phase line diagram, this can give me a lot of information about my dynamics of my system. Let's imagine that this is where I wanted to start. So right here, x of 0. Okay, so if I trace this up, I go to the point on the curve, which is f of x of 0, which is x1. X of 1, right? So all I did was took that initial condition, put it into this thing, and I get some number, right? That's my next point. That's my next, if I check my yeast population after an hour, this is the number, whatever that number happens to be. Okay, that's great, but that doesn't help me a whole lot. What I would like to do is I'd like to keep going. So what I could do is I could find where x1 is on the x-axis. Okay, so how do I find where x1 is on the x-axis so I can trace it up to the curve again? Well, I've got this line y equal to x for me. And so that means that if I trace myself over to the line, wherever I am on that line, this is x1 right here. But then if I trace myself down, that's x1 right here as well, because the line represents the points where the y-axis is equal to the x-axis. So that means that I could restart from x of 1 here. And I could trace that up, and I could find the next iterate on my graph. So this would be x of 2. And now you can see that things are getting a little messy, but now I can basically repeat the same procedure. I can trace myself over, and then I go vertically up to the curve. Then I trace myself over, and I go vertically up to the curve. And what you're going to get is a little tic-tac-toe. And in this case, you can see that you are pushing yourself into the equilibrium point. In this case, xn is converging to the equilibrium point k, right? So as you can see it, you're sort of wedging yourself into this little tiny space in here. You could do the same thing over here if you wanted, right? So maybe you start with too much of a population. Well, then you trace yourself up to your curve. This is your next iterate. Then your population, your model says, okay, you're above the carrying capacity. You want to decrease. Your growth rate is negative now. And we can see that by tracing over to the y equal to x line and then vertically to the f of x line. Same thing. You're going to sort of wedge yourself in, and again, using a different color, you're seeing that you're converging into your carrying capacity k. So, is this always what's going to happen? Well, it turns out no. Things can get very complicated very quickly in this case. So, let's take a look at another one of these pictures. Now, for the record, these pictures are what are known as cobweb diagrams. Now, it comes from this little tracing out that happens in here. For more complex functions, these things start to look like very complicated cobwebs. So I'm going to try and sketch some out for you today so that you can see where this cobweb notation or nomenclature actually comes from. Now, in this case, I didn't specify what the values of r and k are. K doesn't matter, but r does. Because r is going to tell you how much of a slope you have initially here on your function. And really, it's going to tell you where your k value is, your equilibrium, where it lies along the hump. Okay? So here's what I'm going to do. I'm going to use a different value of r. Let's use, I increased r, so this thing is supposed to be up a little bit higher. This is my f of x function. Again, the right-hand side of this. Remember, to do this properly, we have to have y equal to x on the curve as well. Now you can see that my carrying capacity is way over here. right? So I've still got the equilibrium. That never changed, right? Doesn't matter what the value of R is here, but the carrying capacity always persists as an equilibrium. The question is, what happens to the dynamics? Well, we can trace out another cobweb diagram. Let's imagine we start with just a little bit of yeast, okay? So we just start with a little tiny bit. Well, what we do is we trace ourselves up to the curve. That's x1. Then we trace ourselves over to the line y equal to x, and then up to the curve again. Right? So it's a horizontal, vertical, horizontal, vertical. You go horizontally to y equal to x. You go vertically to f of x. Okay? So this would be x of 1. This would be x of 2. Then I trace myself over and up. X of 3. Okay, now is where things are going to get interesting. Because look what happens next. I go over, and now I've overshot the carrying capacity. This is something that didn't happen before. Remember, I always stayed beneath the carrying capacity until I grew up into it. In this case, my value of R is larger. That means my relative growth rate is bigger. So what's happening here, as you can see, is I'm taking way bigger steps from point to point. My yeast is so ambitious. It has a very high growth rate, right? So from hour to hour, it explodes in population. And it explodes so much in population, it overshoots, right? I check it at hour 3. I say, okay, you're below the carrying capacity. I check it at hour 4. Say, what happened? You overshot. You went way over. Well, then it says, okay, well, there's too many of us. We got to contract down. So then what happens? You pull yourself back. You go up. And then now you can see you get this continual process of shooting and overshooting the carrying capacity, right? So you can see it says, okay, way too many of us. Now bring that population down. Then way too many of us, bring that population down. Way too many of us, bring the population down. And what you see in this case is you're essentially spiraling into the carrying capacity K. So again, you're going to find this. You're going to find Xn is converging to K, but it's doing it differently, okay? It's doing it by flipping back and forth over K. This is just like what I showed you on the previous, in the previous video, where I showed you if lambda is between 1 and 2, you get negative multiplications each step, and you overshoot, and you sort of jump back and forth between negative and positive numbers. Same thing is happening here. Our growth rate R is bigger in this picture. I'm purposely not telling you what the value of R is because this is just supposed to be phenomenological. But R is bigger because this graph went up higher. And because R is bigger, you overshoot from step to step. You know, at hour 3, you have way too much crowding. It says, we got to get this under control. We got to call the herd a little bit. And then it goes down at hour 4, and it says, okay, well, we got room to grow. So then we go back up. We say, oh man, we overshot. There's way too many. Go back down. Okay, we got room to grow. Too many. Room to grow. Too many, right? Until it finally finds that nice balance where you have yourself sort of settling into this equilibrium. Now you can kind of see the cobwebness of this as well, right? Now you can kind of see why people refer to this as a cobweb diagram, because you can see it's really sort of spinning out a pretty little cobweb. Let's keep going. Let's keep pushing this thing. Let's increase R even more. Okay, so here's going to be my picture. I'm going to go way up. Okay, so imagine the growth rate is huge in this case. Again, these are just sketches meant to sort of offer up some general ideas for you. This is going to be f of x. Now, what I will do in the link to this, or in the description of this video, I will provide a link to a website which will actually sketch out these Cobweb diagrams for you. So what you could do, for example, is fix k equal to 1 and go through and systematically increase these values of r and see all the craziness that ensues, right? See if you can find, for small values of r, you get this sort of monotone convergence. And then see if you can find the tipping point where you get this sort of, this jumping, this overcompensatory growth where you are jumping but eventually settling in. And now, let's get even crazier. Let's see what's going to happen here. Okay, so again, equilibrium point, even though the picture's not great. Carrying capacity is way over here. Let's see what happens, okay? So we can sketch out a Cobweb diagram for this case. Here's my x of 0. Let's imagine we start with a very small population, just like all of the cases that I played with. Go up. So you have a massive jump in the amount of population you have from step to step, right? R is huge in this case. So your yeast population grows massively from step to step. Then you're way too big. So you got to bring yourself down. So you bring yourself way, way down. But now you brought yourself down so much, you overshot. You said, okay, actually, I think we took out way too many of us. So we got room to grow. Okay, so then we shoot way, way back up. And then we say, okay, well, we overshot here. Now you can see that my picture's not great, but it should come down, maybe way down here. Not the best picture in the whole wide world, but the principle remains. You can see that you're sort of really, really hopping back and forth. And in this case, you are never going to settle into a good equilibrium point. You're always going to find yourself just hopping around and around and around on this picture, okay? So this would come from taking R to be very, very large, right? You could try something like 4 or maybe 6, depending on what your values of K are on top of this thing. But nonetheless, in this case, if I had a better drawing here, this would be chaos. This is an example of a chaotic dynamical system. In this case, things never settle down. The value of R is so large from step to step that you just constantly overshoot and then call the herd way back down, overshoot, call the herd way back down, overshoot, call the herd way back down, and you do it in a seemingly random way. You never really know where you're going in order to make this diagram. And if you actually just kept drawing this diagram, it would start to fill in. I would have so many lines on this thing that you wouldn't even be able to read it, right? At least for my previous 2 pictures, everything gets kind of localized and spirals in this case, into the carrying capacity. In this case, everybody just falls into the carrying capacity. They're all just sort of absorbed into these 2 equilibrium points. In this case, the equilibrium point is no longer absorbing anybody. You can sort of wander around as you wish and keep flipping back and forth between large populations and small populations, below the carrying capacity, above the carrying capacity. Things are sort of happening in a seemingly random manner. And it comes from the fact that your growth rate of your yeast population is so big that you're making enormous jumps from step to step. So again, my pictures don't do it justice. I want you to try and actually do this for yourself. Use the link in the description. Actually pick a bunch of values of R, iterate it up, take some little initial conditions, maybe start really, really close to 0 and see what happens to your yeast population. Now, the last thing that I'm going to mention is that actually in 1913, a German researcher, Carlson, actually tried to, or collected a bunch of data on yeast populations. So this is where the original inception for this simple little exponential growth model that we saw right here came from. The 10% from time step, or from hour to hour, came from some of Carlson's original data. But if you take Carlson's data and you actually fit it to a model, so a model of this form, you can actually find that your yeast population iteration scheme is about 1.56 xn, and then minus 0.00, let's see this, 0.861 x of n squared. Now, what does this actually mean? This means r is equal to 0.56, and this means that k is equal to 650.4-ish. Okay? So that actually gives you explicit values. If you want to, throw those into a Cobweb diagram, you can check out what actually happens to your mapping as you iterate through. And you can ask yourself, if you were T. Carlson actually observing this back in 1913, what would your yeast population do if it was governed by this model? Right? So I'm going to leave that for you. You can draw the Cobweb diagram associated to these values of R and K. You tell me, right? Go ahead and let me know what you come up with. I'll see you in the next video.